Hello, everyone. Thank you for listening to my presentation today. The title of my paper is Optimizing Flow Bandwidth Consumption with Traffic Diminishing Middlebox Placement. My name is Yang Chen, and the other two authors are Professors Jie Wu and Bo Ji. The network function virtualization changes the area with the software Middlebox, or the VNF, which is short for virtualized network function. We use the VNF or Middlebox alternatively in the following presentation. And the purpose of using the VNFS is to improve the performance and enhance the security. Here are three common middle boxes. As the middle box is implemented in software, so it is highly possible to reduce the capital and operational expense by carefully picking up their location among the switch connected servers. So this kind of topic is called the Middlebox deployment. And next, we introduce the traffic changing effect of the middle boxes. The VFS may change the flow rates in different ways, diminishing or expanding. So when it comes to the diminishing effect, for example, the Citrix Cloud Bridge Wide Area Network Optimizer can reduce the traffic volume by up to 80% by compressing the traffic. And as for the expanding effect, one kind of the BCH encoder can increase the traffic rate nearly by 30%. And in this paper, we only focus on the traffic diminishing effect and leave the expanding effect as our future work. So here is a motivating example for our paper. The cylindrical nodes are the switches, and the cubical nodes are the middle boxes. The middle boxes are assigned to servers. They are not shown in the figures for the simplicity. And these servers are connected to the switches in the network. And all flows need to be served by a same type of middle box before reaching their destination. The traffic changing ratio, which is the proportion of flow's traffic rate before and after being processed by the middle box, is 0.5, which diminishes the traffic rate. And we can see there are 4 flows, F1 to F4, and their initial traffic rates are 4, 2, 2, and 2 respectively. The line thickness indicates the traffic rate. So their sources, destinations, and paths are shown in the figure. The paths are predetermined, shown in different types of lines. And we can see that in the figure A, it shows the optimal placement with only 2 middle boxes allowed. A middle box is placed on the V2 to process flows 2, 3, and 4, and another one is deployed on V5 to process the flow F1. We take F1 as an example of the calculation of flow's bandwidth consumption. Its initial rate is 4, and its consumed bandwidth on both links, V5 to V3 and V3 to V1, are 0.5 times 4, which is 2, because of the deployed middle box on V5. Then the total bandwidth consumption of F1 is 2 plus 2, which is 4. So in the same way, we can calculate the total bandwidth consumption is 2 times 4 plus 4, which is 12. However, if we are allowed to deploy 3 middle boxes shown in the figure B, we should deploy one on each flow source because this can reduce the bandwidth consumption in the earliest locations for all flows. So the total flow bandwidth consumption here is reduced to 0.5 times 4 times 2 plus 2 times 2 plus 2 plus 2, which is 8. And we can see that it's actually the minimum one of all the cases. And in this paper, we address the placement challenge of middle boxes and propose solutions for the middle boxes with the traffic diminishing effects in order to minimize the total bandwidth consumptions of all flows. And we need to make sure that each flow gets processed by the middle box. And we have another constraint as the total number of the middle boxes cannot be larger than a predefined parameter k. So here is the mathematical formulation of our problem. The objective is shown in equal 1 is to minimize the total bandwidth consumption, which is the sum of all flows bandwidth consumption. And we can see that a flow's bandwidth consumption is the sum of its occupied bandwidth on each link along its path. And in equation 2, our deployment plan contains all the nodes that with their value of parameter MV as 1. And equal 3 states that the total number of placed middle boxes is no more than the predefined constraint K. And the total number of selected vertices with the deployed middle boxes equals to the sum of MV for all the vertices. This is because when the MV has a value of 1, it means that a middle box is deployed on V. Otherwise, the MV should be 0. And equal 4 requires that each flow to be served by the middle box once and only once. Equal 5 ensures that a flow only can use a middle box on the vertex when there is one middle box placed on. And the last equation shows that each vertex can only place one middle box or doesn't play any middle box. And each flow only needs to be processed by one middle box. So we first studied the general topology. We proved that in the general topologies, our problem is NP-hard by reducing from the classic NP-hard problem, the set cover decision problem. And then we define two functions, the decrement function and the marginal decrement function. For the decrement function, it indicates the decrement of the total bandwidth consumption by a deployment plan P. And the marginal decrement function indicates that the additional bandwidth decrement of processing flows by deploying middle boxes on a new subset S of vertices beyond the current deployment plan P. Next, we proved the decrement function is submodular. The insight of the proof is that it's intuitive that the more middle boxes are placed, the less bandwidth consumption is, since each flow can be processed no later than the previous placement P. Thus, for the decrement function, it is a non-decreasing function and monotone. Additionally, the marginal decrement becomes smaller when more flows are processed. The mathematical proof is included in the paper, so here I omit the details. And we propose one solution called general topology placement, short as GTP. The algorithm GTP initials the placement plan as an empty set, and then it iteratively selects the node with the maximum marginal decrement until all flows are fully served. And we prove that the solution is derived from the classic submodular set cover solution. So actually it's a performance guaranteed algorithm with an approximation ratio as 1 minus 1 over E. And the time complexity for the algorithm is the V square times log V, and the V is the total number of vertices in the network. And because it selects K rounds to place the middle boxes, so which is at most V, and in each round it needs to find the minimum value of all the marginal decrement, which takes a time of V log V. And then we propose two solutions for the tree topology, which is quite common in today's network topologies. And we define two values, F, V, K. It means that the minimum total occupied bandwidth of all flows with K deployed middle boxes in the subtree T rooted at V when all the flows have been fully processed. And another value is PVKB. It denotes that the same value, which is the minimum total occupied bandwidth of all flows with K deployed middle boxes in the subtree of TV when all flows with a total bandwidth consumption of B have been processed. It means that part of flows get processed, not all. And we show that is optimal, and the time complexity is V times log V cube times the largest flow rate, because we need to list all combinations of feasible K and B. K is less than V and B is less than the number of flows times the largest flow rate. And the number of flows is less than log V after merging all flows from the same source. Here is the illustrations for the two values we defined. So for the partially processed situation, we have only one case shown in the top figure. When flows are partially processed with a total served bandwidth B, there is only one served situation. The left and the right subtrees of V are both partially served, and the minimum total bandwidth in the subtree of TV is selected from all the combinations of allocating the total K middle boxes. If the left subtree deploys P middle boxes, then the right one can only deploy the remaining K minus P1 P middle boxes. So for the fully processed situations, we have two cases. So shown in the bottom two figures. In the figure A, the left and the right subtrees of V have already been served by totally deploying K middle boxes before V. And the minimum total bandwidth consumption in the subtree TV is selected from all the combinations of allocating the total K middle boxes. And if the left subtree deploys P middle boxes, then the right one deploys the remaining K minus P middle boxes. So in the figure B, its two subtrees are partially served. So if we want all the flows served, so we need to deploy one middle box on the vertex V to make sure all flows get processed in the subtree. So the minimum bandwidth in the subtree TV is selected from all the combinations of allocating the remaining K-1 middle boxes in its subtrees. And we then propose one efficient greedy solution, which is the lowest, which is called the heuristic algorithm for trees. We define the lowest common ancestor first, which is the lowest vertex that have both vertices V and W as its descendants. And for the details of the algorithm, we first deploy one middle box on each leaf vertex in the tree, and then we delete two middle boxes on V and W if they have the minimum difference of the total bandwidth value. And we place one middle box on their lowest common ancestor. We do this until we deploy all the K middle boxes. So in order to improve the time efficiency, we use the min heap to maintain all the different values. And by using the min heap, the time complexity here is V squared times log V. V is the number of vertices. Then here comes our simulation part. We have two comparison algorithms. First is called random. It means randomly deploy all the K middle boxes in the topology. The second one is called the best effort. We deploy on the vertex that can reduce the total bandwidth of flows most at the current step until all the middle boxes are deployed. And our proposed algorithms, GTPs for the general topology, and the GTP, DP, and hat are for the trees. Here is the topology we used for running our simulations. We use the ARC infrastructure, and we extracted the tree and general topologies from the infrastructure. The traffic diminishing ratio, we changed from 0 to 0.9. And the flow distribution comes from the KDA data center by our packet trees. And here are the simulation results for trees. We found that our algorithm DP performs best for all of our variables. And when K equals to 1, only one feasible placement plan for all the methods. And the traffic changing ratio has the largest impact on the bandwidth consumption. And we found that the algorithm random has the biggest fluctuation during the changing of variables. So for the simulation results of the general topology, we can see that our proposed algorithm GTP always consumes the smallest bandwidth. And we found that the arrow bars becomes smaller than the previous one in the trees. And the bandwidth consumption increases faster in the figure 2 when the ratio changes from the 0.4 to 0.6. When the flow density is lower than 0.4 in the third figure, we see that little difference among the three algorithms. So here we also do the extra simulation on the spam filter, which has a traffic diminishing ratio as 0. We show that it plays we show that the flow density plays a more important role in affecting the total bandwidth consumption than the K. When the flow density doubles from 0.3 to 0.6, the bandwidth consumption in tree increases more than 30%, while the increment is only 25.6% in the general topology. So here is our conclusion and future work. In this paper, we studied the Middlebox deployment problem with a limited number of traffic diminishing middleboxes. We aim at minimizing the total bandwidth consumptions, and we propose several efficient solutions. For the future, we will focus on the traffic expanding middleboxes and may include the service chain deployment problem, which is another set of multiple types of middleboxes. So thank you for listening. Any questions?